Welcome back to STEM Online Academy. My name is Jason Masterakos, for those of you who don't know. And today we're going to be discussing an interesting topic as to why this particular integral looks impossible. Okay, this guy over here in white ink. Right, so I'm going to help you guys see how to solve hard integrals that you wouldn't be able to do normally. They may look really hard, they may look impossible, but they still have a solution. Okay, most of the times people think they don't, but they actually do. This requires some clever substitution and some creativity, I guess you can say. All right, let's get right to it. First off, this integral, yes, it can be a headache. I have to agree. We're going to look at this one here. It says integral from 0 to 1 of ln of 1 plus x dx all over 1 plus x squared. That's what we want to solve. Now, the way we want to go about this, okay, here's how we want to go about this, right? So, now most students will lose too much time on integrals like this. And that's not because the integral is impossible, it's because they choose the wrong substitution. Okay. If you try to brute force this, it feels messy and confusing. But the problem is not asking about brute force, it's asking whether you can see some form of pattern or structure. Okay. Once you do, the whole thing becomes easier, right? So let's look at the integral. You'll notice several things are happening. First off, when you have an integral, uh, everyone has this insight, right? You think, instead of using integration by parts, instead of using power series, instead of be using some trigonometric substitution, at least some form of method through your mathematical checklist. That's what everybody does. And then they deductively rule out um, which one is the correct one to use. And that's exactly where uh, many strong students actually get trapped. Okay, because each of those ideas looks plausible, but none of them would actually work. The ones that I just listed, those techniques would not have worked. Okay, so the exact mistake here, right? So let's name the mistake clearly, okay, in this integral here. Okay, the mistake is trying to compute before asking how the integrand transforms. Okay, that's pretty much the entire lesson of this problem. Is not a computation first integral. Okay, it is a symmetry first integral. Okay? Once you approach it that way, everything becomes lighter. Okay, let's get into the algebra. Okay, the first structural observation is that the denominator is a major clue. That's why I'm sticking to this equation. Hang in there. Don't lose track of what's going on. I don't want you to get bored. Here's where the fun part comes. Okay? The denominator 1 plus x squared is a major clue. Okay? Whenever you see 1 plus x squared in your denominator, consider some sort of tangent type of substitution or some form of transformation. You should know what I'm talking about. Okay? But here, there's an even better move. We want to have a substitution that transforms, right? We want to transform the logarithm in a helpful way and also interacts with 1 plus x squared. Okay. So I've written it here, right? Because the denominator has the express 1 plus x squared. We want to have a tangent type substitution. Okay. And that substitution is in the yellow, x equals 1 minus t all over 1 plus t. Okay. Now, this may look unusual at first, but that is the whole point. Right? The best substitutions often do not look obvious, but they will accomplish a lot of action. Okay, let's go to the next page. Now into the algebraic part of this problem. Okay, let's compute everything in a step-by-step fashion. We know that x, or substitution x, is 1 minus t, all over 1 plus t. Okay. From here, just like any substitution, right, when it comes to integrals, we need to find a differential. So my differential dx is going to be minus t all over 1 plus t all squared dt. Okay. Now we need to compute the 1 plus x, the 1 plus x part of this fraction. Okay. So you'll notice that the 1 plus x is equal to 1 plus 1 minus t all over 1 plus t, right? Because I'm substituting x for that 1 minus t over 1 plus t. Okay, and you can see it simplifies to 2 over 1 plus t. You'll notice that the logarithm was ln of 1 plus x. We now have an expression of 1 plus x in terms of t. Eliminate the x with the parameter as a function of t. Therefore, I get ln of 2 all over 1 plus t. Okay, now I can compute my denominator. Okay, my denominator now, this is just an algebraic deduction, right? Now the denominator will be 1 plus x squared, okay? 1 plus x squared equals 1 plus, all in parentheses, 1 minus t all over 1 plus t all squared, right? That fraction there, this guy over here, right? That's just that x substitution that we substituted in, okay? From that portion there, we want to bring this over a common denominator. So you can see that 1 plus x squared is now all over, is equal to 1 plus t all squared, 1 plus 1 minus t all squared all over 1 plus t all squared. Okay, common denominator. We want to expand. Okay, I'm expanding the 1 plus t all squared and the 1 minus t all squared. Okay, I hope that makes sense, right? So you can see here we have an interesting thing, right? In the numerator and denominator, we have perfect square trinomials. One is an addition, one is a subtraction. I just going to expand and then collect like terms and simplify, right? So from that, we get 1 plus t whole squared plus 1 minus t whole squared. Simplifies to 2 plus 2t squared, 2 in parentheses 1 plus t squared. Okay. Therefore, we can finally substitute our 1 plus x squared as a function of t now because we have our expressions, right? This guy here, right? And the other one upstairs, right? 1 plus t squared, right? So 1 plus x squared is just simplifies to 1 plus t squared in parentheses, highlighting it with an asterisk, all over 1 plus t squared, all of parentheses, the exponent 2. Okay. All right, so we're about halfway done. What we're going to do now, what we want to do now is plug all this into the integral, right? Because the integral that we were trying to calculate is this guy here. So I want to make a parameterization change, right? I'm parameterizing x as a function of t now, okay? Because it'll be simpler to do that way, right? We'll be able to get an integral that we can integrate. Okay, so let's do that. So let's go to the next page. Okay, so the next page, right? So again, since we have this integral here, I'm just repeating integral from 0 to 1 of ln of 1 plus x dx all over 1 plus x squared. We want it, since we want to substitute everything in terms of t here instead of the x, I need to eliminate x as a parameter of t, right? But to do that, if I want to integrate with respect to t, I need to find the limits of integration, the new limits of integration, okay? So the way to do that is to find limits of integration for t, but the only way to do that is to take the upper and lower bounds that we initially had as a function of x, right? X was 0 and x is 1. So substituting x equals 0 from our lower bound gives us into our equation, right? 0 equals 1 minus t over 1 plus t because x was equal to 1 minus t over 1 plus t, right? So x is 0 for the lower bound. Rearranging for t, okay, rearranging for t, I get t equals 1. And then do the same for when x equals 1, right? Substitute x equals 1 there, I get 1 equals 1 minus t all over 1 plus t. If I rearrange and simplify to get t equals to 0, okay? Now that I know my upper and lower limits of integration in terms of t, and I have an expression that I can eliminate my my equation in terms of x. I can eliminate the x now as a parameter of t. Therefore, I get a new integral. Right. This means our integral now becomes, right? It becomes the integral lower limit of integration we found was 1. Okay. Lower limit of integration is when x is 0. That's the lower limit, right? And the upper limit when x equals 1 gave us t equals 0. That's why we start from integral from 1 to 0. Looks strange, but no, that's what it is. Okay. Next, I substitute, as I said, into my ln. So ln is now as a function of t all over 1 plus t, all divided by 2 parentheses 1 plus t squared, parentheses divided by 1 plus t all squared exponents, all parentheses, sorry, all parentheses exponent 2. And I'm multiplying by a factor. I'm multiplying by a factor of negative 2, right? Negative 2 dt all over 1 plus t all squared. You understand what I mean? Because there's a differential there, right? We have to take into consideration our differential, right? Our dx. Okay. So simplifying, now we just need to simplify the algebra inside the integral. Okay. So the way to do that is to look at the integrand. Well, I mean integrand, the function inside, right, of the integral. And that was just 1 divided by the whole thing of 2 parentheses 1 plus t squared, parentheses divided by 1 plus t all squared. Flipping the denominator, you notice we get 1 plus t all to the exponent 2, all divided by 2 parentheses 1 plus t squared. Okay. And then I'm going to simplify this. I'm going to simplify, you're going to get negative 2 all divided by 1 plus t all squared. That gives us that. Okay. And then from there, we actually get, it gives us negative 1 all over 1 plus t squared. Okay. Meaning, if I substitute back into my integral, right, this guy over here, substitute back into the integral, you're going to notice we have I equals integral from 1 to 0 of ln on parentheses 2 divided by 1 plus t dt all divided by 1 plus t squared. And there's that negative sign there. Okay. Because we had a negative in front of our 1 all over 1 plus t squared. Okay. Now, what this flips to, what this becomes, is that I get I equals the integral from 0 to 1 of ln of 2 all over 1 plus t dt all over 1 plus t squared. Okay. So I'm just continue over here. Now, going back to phase 3, you'll notice everything was in terms of t. We wanted to integrate in terms of x. So now we just resubstitute the t's and x's, t's with the x's. Okay. All right. So now, just like on page 3, we got that t. Just replace all the t's with x's. It's the same expression as at the end of page 3 for that integral. So the integral now, right? My integral now just becomes, just becomes I equals integral from 0 to 1 of ln of, in parentheses, 2 divided by 1 plus x with respect to x, all divided by 1 plus x squared, right? Okay. This is the key moment. Okay? This is very important because now the original integral has turned into another integral involving the same type of denominator, and that is the major payoff here. I hope you can see that, like how important that is. Okay. Okay, so now we want to add the expressions. You understand? I'm going to add both expressions. If you remembered earlier, we found that I'm going to call it I subscript 1 and I subscript 2. There's 2 integral expressions. Okay. So I have I subscript 1. Let's start with that. And that's equal to an integral from 0 to 1 of ln of 1 plus x dx all over 1 plus x squared. That's the initial integral I think we wanted to solve. Okay. That's what we wanted to solve. That's the question. However, we found a new transformation integral. I'm going to call it I subscript 2. That's the one above in terms of x. I mean, this one over here. Okay, I'm highlighting. All right, this one over here. Okay, you'll notice that I'm going to call it I subscript 2. Okay, I subscript 2 equals the integral from 0 to 1 of ln in parentheses of 2 all over 1 plus x dx divided by 1 plus x squared. The whole thing is divided by 1 plus x squared. Okay, now here's a bit of a tricky part. How do I know that I need to add 2 integrals? If I'm looking to solve this integral here. So isn't that equal to I2? Why am I adding them? I think that's the major the major question that everyone would have, right? And it will be once I answer it, it's going to unlock your difficulties when it comes to doing integrals that require a lot of back and forth substitutions and all that. The reason for that is because we transformed it. Okay, because we did all those substitutions. So we can actually add the two integrals. Okay, that's a big step here. We can add the two integrals. Okay. So even an integration by parts, you guys probably have seen that before. You had to do multiple steps, and you probably were going in circles. Um, like going cyclically in circles, doing integration by parts again and again, until you realize that one integral is equal to another integral, and then you rearrange it, isolate, and then you just solve it for the same integral. Think of it like that here. Okay, so integration in general, um, when you have a hard integral, can be deductively solved just by using what's the word? Just being a bit. It's not always obvious how to approach them or what technique to use, or it just requires some, not that much, but maybe a little bit, some creativity into solving the problem. Okay. All right. So that's how we're going to do this. Right. So we have I1 and I2. Okay. So we're going to add I1 to I2. Okay. So adding I1 and I2, where I1 and I2 are both equal. So I'm going to call them I. So I plus I gives me 2I. See what I mean? So I plus I gives me 2I. And then I get this integral. All right, it looks nasty and it looks scary. You might be asking, Jason, how on earth are we supposed to integrate that? Like, how are we supposed to get? I thought the point of doing this substitution with the parameter as a function of t will make our integral cleaner and easier to integrate. It will, as long as we apply, um, you know, some logarithmic properties and simplify our expression. So, what I mean simplify the expression, I mean this guy here. Once again, the integrand, right? Take care of the integrand. Okay, so let's look at that. So inside, you'll notice we have ln all in parentheses of 1 plus x plus ln all of 2 all over 1 plus x in parentheses. And this is equal to ln of all in parentheses 1 plus x times 2 over 1 plus x. Because if you're taking ln, let's say some x, right? ln, let's say I call this x, and let's say ln y, I can multiply them. That's why I took their products. And then you'll notice that this is canceling. So I'm left with ln of 2. Okay? That ln of 2. See, I made it much simpler now. Now I substitute that back into my integrand, right? Above, right? You'll notice that 2I equals the integral from 0 to 1 of ln 2 dx divided by 1 plus x squared. Now I can integrate that, but I have to notice what are my constants, what are my variables. I will take my constant out, right? My ln of 2, right? So 2 times capital I, my integral, is equal to ln of 2 is a constant, and I multiply by integral from 0 to 1 of dx divided by 1 plus x squared. This, you should automatically be able to figure out what its integral is. It's arctan. Okay? If you don't know that, just look up an integral table, or you can remember, you can do it reverse, right? If you know that d by dx if you know the derivative of arctan is equal to 1 over 1 plus x squared, you can figure out that the integral of dx over 1 plus x squared is arctan, right? They're the opposites. Okay? So that means that my integral from 0 to 1 of dx over 1 plus x squared is arctan. 10x, and I'm taking the limits of integration from 0 to 1. So this now becomes arctangent of 1 minus arctangent of 0, right? Arctangent of 1, that's inverse tan of 1. Okay, inverse tan. Well, what angle gives me inverse tan of 1? That's pi over 4. Okay, so pi over 4 here. Inverse tan of 0 is 0. So pi over 4 minus 0 is pi over 4. Now I substitute that in. Right? I'm going to substitute that in back into here, right? Because I expanded out the integral of dx1 plus x squared. We still have to take care of the ln of 2, right? That means that my 2 times I is equal to ln 2 times pi over 4. Now remember, I want to solve my integral. The integral I want to solve was this guy up here, right? This guy, ln of 1 plus x dx over 1 plus x squared. That's equal to capital I. But we have a capital I. So we want to solve for capital I. That's what we're looking for. So we divide both sides by 2. And I finally get that capital I is equal to pi over 8 times ln of 2. And that is my answer to our integral over here. Okay. Pretty interesting, isn't it? Right, so we figured out what it is. Now, I want to pause here, say something very important. Okay, if this problem looked impossible at first, that does not mean you were missing a technique. It means you're missing a certain type of, let's say, a perspective. Okay, and that is a very different problem. Okay, because perspective can be trained. It's just a matter of somewhat attitude. Okay, so that integral has a very nice solution. Pi, right? Pi times ln of 2 over 8, as I mentioned. Okay, so this is equal to pi. Okay, so pi times ln 2 divided by 8. Okay, this integral was, so what, let's think of it this way, what this problem was really testing. Okay, this integral was not really testing whether you know integration by parts or integration by whatever, but it was testing whether you can recognize that the integrand might become simpler under a smart transformation. Okay. Remember in another video, I did a video yesterday where I talked about the importance of being able to distinguish between what techniques to use. I was talking about that for courses in general, STEM courses, but it's very important to be able to distinguish what approach to use. Okay. And here I've pretty much mapped that out. So this is a much deeper skill. It's a very important skill, actually. And that's why students often feel frustrated by problems like this. Okay. So you're not alone if you get frustrated because they're trying to solve a structural problem with procedural tools and only the procedural tools. The right question, right, was never what technique do I use first, right? The right question was, how does this integrand want to change? Okay. Once you ask that question, that problem becomes much more relatable. Okay. So this kind of problem matters because in real exams, okay, especially if you take harder undergraduate exams, you do not have time to brute force every integral. Okay, it's really hard to brute force every one of these guys. Okay, you need some approach of recognition, and you need the ability to see when, right? The symmetry matters, right? A substitution creates a mirror version of the same problem. Quite often, a substitution is in integration is a clever way of deducing or seeing a pattern of some sort. And the integrand is hiding a relation within itself. That is where your marks can be saved. Okay. Right. So let me just maybe make extra the page here. Okay, I want you to take note of this, right? You need the ability to see when, right? Symmetry matters. So note symmetry. Symmetry matters. Okay, symmetry matters. Substitution creates a mirror, right? So substitution will create a mirror. Creates a mirror, you can say. Right, substitution creates a mirror. And the integrand is hiding a relation. And the integrand hides a relation. Okay, this is important. Okay, and more importantly, that's where the confidence returns because now you're not reacting to the problem, you're actually scanning it, you're reading it. Okay, so important. Okay, now how does this connect to the bigger picture? This is the kind of structural thinking that appears in with a lot of different applications. Actually, obviously, if you're taking some sort of advanced integration, um, let's say an advanced integration course or mathematical methods course, Fourier analysis, differential equations, right? Differential equations. What else? I'm trying to think what else will come up. Mechanics and quantum mechanics, because integration is applied there. Again and again, the same principle is going to appear. Okay. So the hard object becomes manageable once you choose the right viewpoint. Okay? That's the real habit you want to build. You want to choose uh, the right viewpoint. Okay. So no, uh, not do more steps, but choose better steps. All right. So for my closing today, if this kind of explanation helps, okay, and you want more problems taught this way, I wrote a book actually called Advanced Integration Techniques, okay, specifically for um, serious undergraduates who want structure and not memorize tricks. Okay, that'll be in the description below. There'll be a link there. That'll this you can go to and it talks more about it, whether you're interested, and or if you want focused help when it comes to calculus, differential equations, um, or even physics as well. I'm also a physics coach. I also work with students on one-on-one personalized lessons. Okay, the links are all below. One is in my link tree, and one's in personal site. Personal site has more detail, but anyways, so no pressure. Just use what helps. Okay, doesn't matter which one. So the main lesson here is simple. This integrand, or this integral, sorry, did not require more force. It required more conceptual insight. Okay. Once you see that, hard problems stop feeling as what's the word? That's the word I'm looking for. Hard problems don't feel as hostile. Okay. They start feeling readable. Okay. So if you like this video, like and subscribe. There'll be plenty more videos coming up. The next one, I will be talking more specifically about my brand and how we can help you with the services that we have. That'll be hopefully tomorrow or coming back next week on Tuesday. We'll see. Depends if I put it up. Okay. So don't forget to like and subscribe, and I'll see you in the next one. Bye bye, guys.